Okay, so last week we went over the last bits of relativity. We talked about mechanics. We talked about the causal structure of Minkowski spacetime, Minkowski orthogonality. What exactly do we mean by contravariant and covariant? Covariant / contravariant with respect to what exactly? So hopefully you'll now have a better understanding of what it means when we put a superscript or a subscript, and then that should really wrap up all the mechanics that we need, and the general math infrastructure that we need to start tackling electricity and magnetism in a relativistic manner. So the relativistic E&M is built on only a handful of physical concepts. So if you go to Maxwell's equations and the Lorentz force law, you see that there's only 4 Maxwell's equations, and then there's the Lorentz force law. That's pretty much it. And then Lorentz force law, of course, I grouped the Coulomb force and the Lorentz force, V cross B and E. I grouped them together as one combined Coulomb Lorentz force. That's really it. So in terms of physical quantities that we have, so we've got the electric field, we've got the magnetic field, we've got the scalar, the charge, we've got current density, and then we've got the force. That's it. These are all the things that we need. Now, of course, we were able to make a lot of useful simplifications. For instance, writing Maxwell's equations in terms of potentials allows you to reformulate them, and then you get what is equivalent to a wave equation for the vector and for the scalar potential. So then, instead of describing Maxwell's equations in terms of rho and j causing an E and B, you get a rho and a j causing a phi and an A. Now, as you have seen now, when we start putting together a relativistic description of nature, we try to combine temporal and spatial parts. So we always take one thing and another thing, and then we make that part of the same object. So, for instance, we made the gradient operator out of the classic Nabla operator and the DDT. We combined the momentum with the energy to create the momentum 4 vector. And so we're going to try to do that in relativity as well. So the question is really, well, what are the things that you need to combine? So the first thing we need to do is we need to talk about sources. That's the easiest way to do, because we can talk about sources as just moving or stationary charges with some kind of a density or some kind of a velocity, and we don't even need to talk about the fields that they cause. We can just talk about how they're related to the underlying spacetime. So we have really only two types of sources. We've got charge density and we've got currents. So you should not be too surprised that we will combine the charge density and the current into one 4 vector for the current. That's what we're going to call the current 4 vector. So I'll walk you through how we're doing that and what's the rationale for that, and then we'll do that. And then having established that, we'll use the D'Alembertian, which is the that operator that you make out of the gradient squared, or the Laplacian squared generalized to Minkowski 4 space, and we'll say, well, once we have a 4 current, we can also describe a potential that results as a 4 potential, which is then going to be a combination of the scalar potential and the vector potential. So now we will have a 4 potential. So that'll be really good. And then we'll be able to describe, and that's basically already Maxwell's equations, except we haven't put the fields in yet. So when it comes to fields, it's a little bit more complicated, and I don't think we'll do fields today. I think we'll go to fields probably next class, and then we actually have to do the stress tensor combined with energy density and Poynting vector. Those also become one concept, but becomes bigger and bigger and bigger. Now, The issue with the electric and the magnetic fields are that it looks a little bit less clear than if you talk about than if you do this with potential. So that's why we'll do potentials first. And then hopefully by the end of today, I'll have shown to you how you can then work backwards to that first motivation that I cited as a motivation for talking about the relativistic treatment of E&M. And I'll be able to show you, and hopefully you'll agree with me that you finally understand now why this is, that the Lorentz force has this really weird cross product. And the trick is that you just need to get rid of the magnetic field through a Lorentz transform. And that's the recipe for today. Any questions? For current. All right, that's what we will do today. So, so let's say we have some kind of a charged object, rho, and we've got some frame, K, and in the frame K, that's the co-moving frame. It is stationary, so because the frame is co-moving. Whereas when we are in a frame that is not co-moving, so for instance, we can call that the lab frame. So K prime, the lab frame, which you could say as being at rest with respect to that particle that's moving. But of course, you understand, relativistically speaking, that statement doesn't make much sense. But that's how you can, in your head, you can try to keep them apart. One is a lab frame, the other is the moving particle. It does sometimes help to think about it that way. So so then you have this particle, but now it's moving with some velocity v, and that of course constitutes a current density J. Now in the K prime frame, we should make sure that we label all of these appropriately. So for instance, we're going to call this, a rho prime, and we'll have some velocity v. Now that velocity v in the K prime is just v, whereas it is 0 in K. I'm not going to put a prime over it because it's actually it's the vector field. It's the vector quantity that actually gives you the transform. So in rho prime it's v, and in rho it's just 0. So I'm not putting an accent here because really what you're doing is you're changing the velocity from v to minus v. So we'll just leave that one as is. But of course, now we have a current density here, which is now J, which is, that's of course scalar, rho prime v. Okay, so there is a Lorentz transform that takes you from here to there. All right, so there's a Lorentz transform with some speed v, and when you do that, that speed, there are two things that happen when you take that transform. So I'm going to write that down. Physically, two things happen when we take the Lorentz transform from K to K prime. One is that rho changes due to length contraction. All right, because rho is charge density, and we're changing the structure of space-time, right? We're changing what we call 1 meter, so rho is going to change. So so what does that mean? Well, that means that rho prime is going to be equal to gamma times rho, and I think I had that color coded as just black. Yes. I might as well do it in red. Okay, times rho. Okay, so make this red then as well. Okay, so this has nothing to do with E and M yet. This is just saying, you know, we just rescale the underlying space-time. Okay, so that's the first thing that happens. And then the second thing that happens is a moving charge by definition is a current or a current density. And you cannot have one the moving charge, without the other. Okay. Now, of course, if this moving charge happens to be neutral, then of course current density is also zero. Of course, there are trivial zero cases, but that's not what we're talking about. So so that means that in the K prime frame, there's a current density J prime that is equal to, by definition, you know, it's going to be rho prime times V. And rho prime, of course, is from here. Is going to be gamma rho times V. Oh, it's going to be very colorful. I like it already. Okay, this, of course, comes from here. Okay, so we are now able to describe that that current density in the primed coordinate system as something coming from the original charge density in the co-moving frame. Now, remember that when we have a Lorentz transform, so when we take a Lorentz transform that takes you from some A to A prime, some 4-vector physical quantity, so A mu to A mu, and let's do this with just time and x, then you should remember that there's the A primed 0 and the A primed 1, so that will be the x component, and then this is your Lorentz transform for the transform from the co-moving frame to the lab frame, so there's no minus there, because we're basically doing the inverse of what we usually do. And we take an A naught and an A1. Now, if you look very carefully, you'll see that the current, this A naught multiplied by this gamma times V ends up over here. So what we can try to do is we can say, okay, let's call this rho, and let's call this J, and then see where we end up with. So let's say, so let's define, because then this transform works out, right? Everybody sees that, hopefully. So let's define the current J mu, and it is it's rho J vector, and in if you don't have when C is not 0, C is not 1, then it's actually it's C rho and J. Okay, just so you know that that's where it goes. So if we use that definition for the current, then we have a J mu is rho and 0. That's in K prime. Actually, let me stay consistent. Let me do that in red. So in K, we have J mu. So your rho, and then 0. Put a vector over here. And then in K prime, we have J prime mu be rho prime, and then J prime. Okay. So that will work, right? So we can now take a take the Lorentz transform and say J, which is going to be rho prime, and then J prime. I'm doing shorthand. Okay, Lorentz transform. Oops. Lorentz transform, of course, is going to be no. It's going to be mixing up my. Okay, that's your gamma, gamma v, gamma v, gamma, and this is your original rho. Now, come on. It's supposed to be red. Rho 0. Okay, so that works. That is going to work properly as a 4 vector. All right. So the trick here is that, of course, this operator, which is ddt, oh, come on, dt gradient, or if you want to do it, del t, del I. If you let that act on the current 4 vector, you get the continuity equation, right? Because you get a ddt and a gradient dotted. So this is a 4 dot product if you want, with this is rho and this would be j. So that means you'll get ddt of rho plus the gradient, not gradient, sorry, divergence of j being 0. Okay, now we've talked about the continuity equation many times now, and we know that this equation expresses charge conservation. Now the laws of electricity and magnetism say that this equation needs to hold if we include the displacement current in Ampere Maxwell. Now, when we include the displacement current and we therefore are able to get to this charge conservation law, we don't actually specify a specific inertial frame for which this must hold. In fact, E&M doesn't really have a preferential frame because it works in all sorts of frames, because actually it's a Lorentz covariant description of nature, and we don't really have a preferred frame of reference. So when we say charge is conserved, we mean its charge is conserved in every frame of reference. So this holds, well then, so del mu j mu equals 0 holds in all inertial frames. Now, the other way to see that holds is to see, well, actually, that's not really an accident, because that's covariant, right? And this is contravariant, which means that when you contract a covariant and a contravariant term, the result is going to be invariant. So that 0 is going to be invariant, which means that if this expression is invariant, that means that this is another way of saying that charge is conserved in all inertial frames. And it does make a lot of sense, right? Because we started defining this current 4 vector as, well, let's just take a charge and let's make it move. And we said, well, that current must be due to that charge moving. So we didn't actually when we set this up, we already kind of set us up for charge conservation, because we did not describe currents as magically appearing out of nowhere. We said currents are because charges are moving. So it makes a lot of sense that charge is conserved, but it's always nice to see. The other thing that this expression indicates is that, well, we know that del operator in the for del operator is covariant, and we know that the thing on the right must be an invariant. So therefore, it makes sense. We have afterwards basically said, well, it does make sense. Oops, sorry. Help. Also validates that J mu is contravariant. Okay. Now we already had that set up, but it's nice to see that there's, as far as compactness goes, this is very, very small. You could also have written it, by the way, you could write it as J mu comma mu is equal to 0. Or I saw some of you write J mu 0. That's also fine. And indeed, you can take del mu and contract it with the metric tensor, call it G mu nu, and then we get a del mu. And we could do the same thing with a J mu and bring it down with the metric tensor. And then you get a J lower mu nu. And then you can write this as del mu, J nu, oops, sorry, J nu. And it would still be 0 because it's still an invariant. And all we're doing when we're moving these indices up and down with the metric tensors, that we're inverting the spatial parts. And if we do two inversions, because we bring the spatial part of the gradient operator, we give that a minus sign, and we invert we put a minus sign in front of the spatial part of the current 4 vector. Those two minuses are going to cancel. So that's just saying the same thing. Now, finally, the book makes mention of the following, which I have not seen myself too much, but there is a law that says that for every tensor for which the divergence equals 0, there is a conserved quantity. I don't know if we'll find more of these examples, but this is a good thing to know. So in this case, the divergence of the 4 divergence of the current 4 vector is 0, and that implies charge conservation. So that's what we mean. Apparently, there's a more general. That's a specific instance of a more general law. All right. Next up, the 4 potential. So our entrance into this. Oh, this is crummy. Hang on. I can do better. The 4 potential. I don't know why it's so hard to write straight on the iPad. See, I'm doing it again. Okay, whatever. So the 4 potential. Our entrance into combining the potentials, scalar potential and the vector potential into a single 4 potential is the following. So remember in the Lorentz gauge, by the way, there's no T here. No T. We talked about this before. In the Lorentz gauge, which is that the that ddt of phi equals minus the divergence of A. In the Lorentz gauge, we were able to write Maxwell's equations. Sorry, the Maxwell's equations with sources, and that is, Ampere Maxwell plus Faraday's, sorry, not Faraday, plus Gauss's law. In the following form. So we got the D'Alembertian, or we can write it as ddt squared minus the Laplacian squared, or we can write it like this. Let me actually write this new. All of those acting on phi was 4 pi rho. And then we also had, same situation, Laplacian generalized, aka Lambertian, nu, acting on the, and of course, there's usually a C here, but the C is 1 right now. So we know that now rho and J are part of this current 4 vector. And we know that this is an invariant, and that's an invariant operator. So we can actually combine these two in one go. We can say, let's call this del nu, and we can write this as phi, a vector, is equal to 4 pi, and then this is rho, and this is J. And of course, rho and J together are the 4 current. So that means we can write this thing as the 4 potential, A mu. Now this thing, that's the 4 potential. Which is just phi and the vector potential, and then we're done. And we're absolutely allowed to do that because 1, this is a 4 vector. Oops. And 2, this is an invariant operator. So we have an invariant acting on something that comes out as a 4 vector, then we can write that as a 4 vector. So the potential, or the 4 potential, is a 4 vector. So now we have taken 2 of Maxwell's equations and written them in 1 Maxwell equation. So now we have Ampere Maxwell plus Gauss. So we basically have the Ampere Maxwell Gauss equation, which says that del nu, A mu is 4 pi J mu. There we go. So from 2 to 1. This is at some point people got really annoyed with all the 4 pi's flying all over the place. So there are different coordinate systems in which you can get rid of your 4 pi's by doing a modified CGS system, which I think is called the Lorentz Heaviside system or something. And then this thing becomes even smaller, but that's it's really not relevant. And of course, you can also write this as, because it's an invariant anyway, so you don't really need to explicitly write the write that del del. So yeah, that's two Maxwell's equations rolled up in one. But of course, this is in the Lorentz gauge. Right, so, but this is in the Lorentz gauge. So we have to ask, what about gauge freedom? Oops. Or gauge transformations. Okay, so remember, we could do gauge transformations. Phi becomes phi minus ddt of phi. And we can write A as A plus the gradient of that. Oops, not phi. It's, of course, psi. Psi. And I'll let you work on that. So write this with a mu. That's assignment number 1. And assignment number 2, oops, write the Lorentz gauge with a muse. Okay. Okay. Let's see. Let's do this one first. So this one's a little tricky because of the signs here, right? So if we want to take, let's say, some a prime mu and map that onto a mu plus or minus something, right? So plus minus some del of psi, that would be the ideal kind of situation. The first thing that we run into is that, if the thing on the left-hand side is supposed to be contravariant, then the thing on the right-hand side is also supposed to be contravariant. The second thing that we're running into is that usually, this operator, right, this del operator is just ddt, and then the gradient, both with the same sign, whereas this gauge transform requires the subtraction of the ddt and the addition of the gradient. So if you go to the contravariant, you get ddt, and you get minus gradient. So then it works out. So then you put a contravariant here, and then you put a minus there, and then everything works out. All right, so then you get the proper sign. You get the minus ddt for the time component of the potential, and you get plus the gradient of the spatial part of that, the regular gradient. Okay, so that's tricky, and it's important that you get those right, as you can tell now, right? So and fortunately, nature helps us here, right? Because you're trying to put it into a 4-vector form, and just by forcing yourself to have the thing in the same nature on the left-hand side and the right-hand side, it forces you to choose the right del operator, which is that's a nice thing of nature to do. Okay, so the nice thing is that it works out now. So once contravariant, always contravariant. So that's this. All right, so Once contravariant, always contravariant. So the transforms that you're allowed to do to the forward potential will preserve the contravariant nature of the forward potential. So that's nice. Okay, now let's do the second one. It's actually a little bit easier. So we know that the del operator is just ddt and the gradient again. Then the Lorentz gauge, where did I write the Lorentz gauge? Yeah, there. So if you rewrite this, you can just write this as 0. It's the exact same, right? Because this is ddt of A0 plus the divergence of a vector. And of course, A0 is phi. So the whole thing works out. So that's the Lorentz gauge. And what does it mean when we write it like this? It means that once in the Lorentz gauge, always in the Lorentz gauge. Oops. Because that expression is independent of the Lorentz transform. So once you're there, once you pin it to that gauge, you're always going to be in that gauge. One thing for which you cannot do this is the Coulomb gauge. Coulomb gauge, where we said that the also the transverse gauge, the divergence of A is 0. You can't really write that as a 4-vector relation that makes sense in every coordinate system. So this you will have to continuously adjust. If you pick one coordinate system and you set your divergence of A to 0, and then you do a transform to a different coordinate system, you have to adjust everything. So that's why you usually don't see the Coulomb gauge once we start doing relativity. All right, the Lorentz force. Or where do those cross products come from? Okay, so now we have in our hands the tools that we can use to describe where that Lorentz force comes from. So let's see how this works. So for instance, we have a current carrying wire. So this is our current carrying wire, and some current I. And of course, that current carrying wire is going to generate a magnetic field. It's going to curve around like this. So that's your B field. And we're doing this in the let's call this frame, in the K frame. Now, let's say that magnetic field, this is the easiest way to do it, but let's say that magnetic field is now interacting with a charged particle. So I'm going to put some kind of a charged particle here, Q, and it's moving with some velocity V. Then we know that that there is going to be a Lorentz force that's going to go in this direction. So that's going to be your Q V over C crossed with B. Okay, so that's your setup for the classic a particle being deflected by a magnetic field through the Lorentz force. So if we analyze this in the K frame, we have to acknowledge the fact that this wire So this wire is neutral, yet carries a current. Oops. Yet carries a current. So, so if it carries a current and it is neutral, that means that there are two species of charges that we need to pay attention to. We've got positive charges. So the positive charges here are moving. And then we have negative charges that are not moving. That's in the wire. So these are moving, and the negative charges are not moving. Honestly, you don't really even need to assume that the positive charges are moving and the negative charges are not moving, as long as you're consistent with your signs. As long as you have charges that are somewhat different in their charge and they're moving with respect to each other, you can make this into a current carrying wire that is neutral in K. Okay, so let's say the positive charges. Oops, let me put this down here. So the positive charges are moving. That means that in K, that J mu, we're going to write this as rho plus, and our J plus. Actually, let me use subscripts, because otherwise we're going to run into collisions with our quadrivariants. Okay, so the positive charges are moving, and the negative charges are not moving in K prime. So that means that J, so this is J plus, J minus mu is rho minus, but it is not moving, so that's 0. Okay, so adding these together, we get a current in K prime that is, rho plus, rho plus rho minus, and then J plus. But of course, that is 0, and that is going to be J vector, because that's the current that is actually being carried by the wire. But now we have it set up in such a way that it makes sense. Okay, now in K prime, so K prime, which is co-moving with the charged particle Q, we have to transform that to a J mu. So that would be J mu, and it will be derived from multiplying this thing by, let me see, so it's gamma minus gamma v minus gamma v gamma. We're doing a Lorentz transform now that we're going into the frame of the moving particle, right? So then there's minuses there. So if you apply this Lorentz transform, so this is your Lorentz transform. If you apply this Lorentz transform to your 4 vector, you get minus gamma v j, and then you get gamma j vector. So that's your 4 current in the frame that is co-moving with the particle. Okay, so this is important. Before, we had a neutral wire, that's here, and now we have a charged wire. And hopefully you can already see what's happening. So in K prime, this wire is negatively charged. What does that mean? Well, in K prime, so let's draw this. The wire is negatively charged. So what does that mean? Well, we have the wire here. There's still current, but that's not what we're talking about. We're talking about the fact that now this thing is negatively charged. And we still have this particle here that's Q, but it's no longer moving because we're in K prime. K prime, go moving. And this thing is stationary. All right, so there might still be a magnetic field here, some B prime, but this is irrelevant. B prime is irrelevant. I can't write anymore. Irrelevant, since V is 0 in this frame, right? The particle's not moving anymore, so there's really no Lorentz force. So we have a positive particle, and that positive particle sees a negatively charged wire and is going to be attracted in that direction by that force. Okay, how big is that force? Well, the force here will be F prime. It would be Q times E in the primed field. Now, E in the primed field would be the field of a charged wire with linear charge density lambda. So that's lambda over 2 pi r. And lambda in this case would be rho prime times the surface area or cross-sectional area. So let's say this thing has a cross-sectional area A. Now, the cross-sectional area A of this wire doesn't actually change because the length contraction is only occurring in the direction of motion of the particle. So A is not changing, so A we can leave it unprimed. So A is A prime, or we can leave it unprimed. And now that's the force. And we know what rho prime is because it comes from here. Right. So that's going to be Q rho prime, which is gamma Vj A is a minus over, let me see, 2 pi r. 2 pi r, all right. And J times A, of course, that is the current. So this is Q minus Q gamma V I over 2 pi r. Okay, so that's our force. So the force in this frame already has the right things that we need for this Lorentz force to work. You see that if we change the sign of I, so we get the current to go in the opposite direction, then the magnetic field also points in the other direction, and therefore the force should also go in the other direction, right? So I changing sign there already takes into factors in properly how the E field would change, and therefore also what the force would do. Also, if V were to go in the opposite direction, we would also flip the sign of the force, right? Because now your QV cross B, your V is pointing in the opposite direction. You're going to change the sign. So this works already for gives us already the important parts of the Lorentz force. More importantly, this force is perpendicular to V. And the force is perpendicular to V because length contraction occurs in the v direction and creates a charged line, and then the force is going to be towards that charged line. Charged line. So that's why it goes in a direction that is perpendicular to the motion. Okay, now finally, in the unprimed system, the force would be Q V B, and B, of course, would be I over 2 pi r. All right. Now, the only thing we're missing is a gamma, and that comes from the force transform. So if you go from F to F prime, then your Fx prime is actually your Fx. Your Fy prime is actually gamma times Fy. Your Fz prime is gamma times Fz, and that is because your 4 vector for the force is gamma v dot f and gamma f. All right, so the force in the direction of v does not get changed, but the ones that are not in the direction of v do get changed. So now finally we have them together. There's a minus sign missing here, but that's just because I wrote the Lorentz force in scalar form. So you see that putting these two together, so this one, and this one, so times gamma is the same. So minus minus, just to get the coordinates right. And that, ladies and gentlemen, is why the Lorentz force works.